Ideal versus real machine. Following the definition of thermodynamics temperature as this relation, it was noted that the thermal efficiency of a Carnot cycle heat engine is for Carnot QH minus QL on QH. Input energy, output energy. Input of QL on QH or equals to TL on TH. It is also follows that a Carnot cycle operating as refrigerator or heat pump beta equals to QL TL on TH minus TL beta prime is for a refrigerator and for a heat pump. TH on TH minus TL. For all three efficiencies stated before, the first equality sign the definition with the use of the energy equation and thus is always true. The second equality is valid only if the cycle is reversible, that is a Carnot cycle, and real engine, refrigerator or heat pumps will be less efficient such that these efficiencies that we have three efficiency or heat pump, refrigerator or heat pump, heat engine. Now heat engine subsequently, refrigerator and heat pump. Will be less efficient than Carnot cycle. with same temperature. Or we can say that eta real thermal eta real QL on QH minus QL TL on TH minus TL beta real QH minus QL for L equal energy refrigerator and heat pump. A final point needs to be made about the significance of absolute zero temperature in connection with the second law and the thermodynamics temperature scale. Consider a Carnot cycle heat engine that receives a given amount of heat for a given high temperature reservoir. As the temperature at which it is rejected from the cycle is lowered, the net work output increases and the amount of heat rejected decreases. In the limit, the heat rejected is zero and the temperature of reservoir corresponding to this limit is absolute zero. Similarly, for a Carnot cycle refrigerator, the amount of work required to produce a given amount of refrigerator increases as the temperature of the refrigerated space decreases this temperature. Absolute zero represents the limiting temperature that can be achieved, and the amount of work required to produce a finite amount of refrigerator approaches infinity as the temperature at which refrigeration is provided approaches to zero. This expression approaches to zero. We have the infinity coefficient of performance COP. In the previous discussion, we considered the constant temperature energy reservoir and used this temperature to calculate the Carnot cycle efficiency. However, if we recall the expression for the rate of heat transfer by conduction, convection, or radiation in the chapter 4, they can be written as Q dot equals to conduction. The constant C depends on the mode of heat transfer. Conduction C equals to beta X. Convection C equals to HA, and radiation C equals to epsilon sigma T infinity. For more complex situations with combined layers and modes, we also recover the form in the equation of the rate of heat, but with a value of C that depends on the geometry, material, and mode of heat transfer. To have a heat transfer, we therefore must have a temperature difference so that the working substance inside the cycle cannot attain the reservoir temperature unless the area is infinitely large.